Hello class, my name is Stephen Peterson. I will be presenting on an article I found called Cybersecurity Threats Detection and Internet of Things Using Deep Learning Approach. It is by Farhan Ullah, Hamad Naeem, Sohail Jabbar, Sheikh Zab Khalid, Muhammad Hassan Latif, Fadi Al-Turjman, and Leonardo Mostarda. The introduction. The Internet of Things connects systems, applications, data storage, and services that may be a new gateway for cyberattacks as they continuously offer services in the organization. Malicious attacks are more easily abrupt due to the growing number of IoT networks. The malware attacks are usually planned to infect the privacy of IoT nodes, computer systems, and smartphones over the Internet. Many types of research have shown that every software contains plagiarized source codes in the context of logic with a range of 5% to 20%. Alright, to explain IoT. IoT is short for Internet of Things. Internet of Things is the interconnection of physical moving objects, things that through the internet embedded with electronic chips, sensors, and other forms of hardware. So pretty much your cell phone, your computer, Nintendo Switch, anything that has a hardware that allows it to access the internet. It could download stuff, come in contact with anything that can be posted on the internet. Cool fact I found on my second reference is 98% of all IoT device traffic is unencrypted, putting your personal and confidential data at severe risk. The Internet of Things security can be understood as security strategy and protection mechanism that specifically safeguards from the possibility of cyber attacks on IoT devices that are connected to the network and purposely built for a fixed set of functionalities. Alright, so the problem and the proposition. Currently, software piracy and malware attacks are high risks to compromise the security of IoT. These threats may steal important information that causes economic and reputational damages. The article states that the proposition combined deep learning approach to detect the pirated software and malware infected files across the IoT network. The TensorFlow Deep Neural Network is proposed to identify pirated software using source code plagiarism. So I will be going over two studies, one using the TensorFlow and one using a mailed in 4-question answer stat. Alright, so the two main challenges are software piracy. So currently every third installed software application is pirated. That's a 33% chance. So the wide availability of open source projects make it easier for the so-called cracker to copy the original idea and design their own software accordingly to what is already out there. The detection of pirated software is among different types of source codes is a challenging task because each source code has different syntax and semantic structures. So you won't see much of the same. Now, so the second one is malware detection. Malware is continuously generating, updating, and trying to manipulate. This makes the detection more challenging. So this is also why sometimes, like say you have your email. Most of the time, spam is going to go to the spam folder, but sometimes spam is going to get in your inbox because as hackers and people who do this stuff get smarter, they can find a way to send their spam or their malicious stuff to pass through the detection and get into your inbox. The high computational cost is also a problem. The high computational cost is needed regarding texture feature mining using malware visualization do not perform well with extensive malware data analysis. Alright, so the proposed methodology. An architect model for cybersecurity threats and protection measures in industrial IoT. So I will be showing you the model coming up soon. It is composed of 4 databases that are implemented in cloud storage to process the two problems, the malware binaries and the software pirated files. Alright, so the other one will be take the source code from Google CodeJam and analyze the proposed methodology for software piracy using weighted values. And the main goal is to catch the pirated software from different types of source codes. Here it is. Alright, so you have your 4 databases right here. And if you do the pirated malware files, it will lead to the 4 steps: the pre-processing, the tokenization, the token weighting, and the normalization. And the layers, I will get into that soon. Here we go. The malware threat detection. Data pre-processing. Color images are generated from raw binary files to transform the malware detection problem using image classification problem. Differentiates the proposed research from state-of-the-art methods in which malware binary files convert into grayscale images with 256 colors. And the deep convolution neural network proposed to conduct in-depth malware data analysis. Now here's the layers. Alright, so the convolution layer. So with malware threat, the convolution layer is used to decrease the noise and give better signal characteristics. Convolutional kernel width, the number of hidden units, our learning rate, are optimized to get maximum accuracy of the proposed deep learning model. From there, the pooling layer is used to decrease the data overhead, preserving useful information. Then we move to the fully connected layer. It's used to convert the 2-dimensional array into the 1-dimensional, and then input it into a specific classifier where they are then identified. Right. The software piracy threat detection. They use software piracy methods to identify source code similarity. The pre-processing techniques are used to break the source codes into smaller pieces for deep analysis. So they will convert the codes into meaningful information or remove noisy data, which I talked about in the current slide. The data is cleaned used from undesirable details, so the special symbols, your constant, your stop words, pretty much key phrases. A tokenization process used to transform the clean data into useful tokens. That's why it's called tokenization. The stemming root words and frequency constraints are used to mine more valuable features. Then we get to the weighting techniques, which are used to zoom the contribution of each token. Now we get into TensorFlow. So, TensorFlow is a machine learning system which is used for higher level computations in complex environments. We can implement different types of machine and deep learning algorithms by calling specific application programming interfaces called API of the TensorFlow. It contains different types of layers which can be configured for complex computations. They training the data and supervise the state run of each function. It integrates various types of computational APIs to design and extend machine learning approaches for larger scales of data. Example, GitHub framework. And I think we can all be honest and say that we've used stuff off of GitHub to cheat off of get some good grades. This framework trains the model automatically based on input, hidden, and output layers with different activation functions. These types of algorithms can be configured and run from small devices to big networks. Now to the results. So this one is the Google code, which was mailed in. The P1, the P2, and the P4 on the x-axis denote the programming solutions of 4 questions, respectively. Then the weighting values of each source code are given on the y-axis, which will be in a range of 0 to 70. Each programmer solved 4 different programming problems, so we have 4 different outputs and 4 different variables. The second and third are configured as hidden layers to improve accuracy. The dropout layer is configured with input in each hidden layer to overcome the overlit fitting problem. As you can see, most of them have very similar answers, except if you look closer to this, you'll see that 4 and 2 and 1 and 3 are more closely related. But their biggest differences are all from the beginning, where all of their data really ended up being in the lower, but 2, 4, and 3 have a lot more data near the bottom than 1 does. So you can tell their differences in their outputs. Now we get to the statistical output. So they use the image ratios that are taken in 224 by 224 and 229 by 229 respectively. So they selected 14,733 malware and 2,486 benign samples from the Leopard mobile dataset. So using the 229 by the 229 image ratio obtained, they were able to get a 97.46%, pretty much a 97.5% testing accuracy with 36S. I think it's 36-second computational time, which is pretty quick if you ask me for that many files for the Leopard mobile dataset. And 90% of the classes are predicted for malicious files with 10% misclassification areas, which 90% is not bad, but 10%, that 1 in 10 is pretty bad. But similarly, 99% of benign classes, which is your smaller 2,486, had a 99% with a 1% misclassification, which is good, but they still were not able to get the perfect 100. So to conclude, the results show higher percentage success. However, they are still unable to successfully prevent all the malicious malware from being passed through IoT networks. And malware detection for unknown set of malware is a big issue. Further, they will try to propose another algorithm that can detect malware for unknown malware families. The experiment was still not 100% successful, and therefore they will have to try a new approach. And these are my references. Thank you.